So just continuing the video from before, and I'll put the link to the paper in the and to this presentation in the video description. So we now know that the moon is sterile, but in the early days of Apollo we didn't know this, and Carl Sagan discovered that the ice trapped below the surface could be liquid at depth just deep enough for organics surviving unaltered, and there's his hypothetical bind there. And then Curiosity has indirectly and that was why Apollo had to take all those precautions. We now know it's sterile, that the layer doesn't exist. It would have been trapped in some way, and then the water would have been liquid, and there would have been some organics there as well, and then spores would have got to the surface, and then Apollo could have returned those to Earth. So it's certainly possible, but our current moon isn't like that. With NASA's Mars, though, Curiosity has indirectly detected binds just 5 centimeters below the surface, and some even, that's in daytime, some even on the surface just before dawn, just after dusk, especially in winter. And this water is too cold for terrestrial life, but except possibly very slow reproduction taking thousands of years, there isn't a hard limit going down to cold temperatures. But I think even for that it's really rather cold. But biofilms could retain the water through to daytime, and Mars also has chaotropic agents that can, such as perchlorates, that can speed up metabolic processes. So there could be native life in the form of biofilms. So then we have the question about what if identical Martian life could have got to Earth, then we could bypass the whole process. And that's the reasoning used for comets, sample returns, because there's plenty of material that comes to Earth from comets. But Earth doesn't get samples of dust or salts from Mars, so this life can't have got to Earth. The meteorites we have all come from at least 3 meters below the surface, and where it's believed to be far too cold for life and sterile almost everywhere. And theoretical studies also show that's where they should come from. Most present-day terrestrial life couldn't get there, even inside a meteorite. Charles Cockle, the astrobiologist Charles Cockle, found that most photosynthetic life would be killed by an instantaneous shock. It's not just acceleration, it's a sudden change from being at rest to suddenly accelerating, and that would kill most photosynthetic life. However, even the most hardy life couldn't get here by transfer of surface dust, because even if any of the dust and salts got into orbit, then most of your is going to go up in the, get dispersed in the atmosphere, but they also go through the atmosphere as shooting stars and fireballs. Even little rocks go through it as fireballs and again be sterilized, and then again on the entry to Earth as well. And then you've got cosmic radiation and solar storms. So there could well be life on Mars. In fact, any life that's on Mars in the binds, it's not at all likely it's got to Earth. And only way back some very distant ancestor. And then, so Mars also, it could have uninhabited habitats, and then the many terrestrial microbes couldn't do it, like photosynthetic life. So many Martian microbial microbes that can't get to Earth at all in that way. And Charles Cockle suggested that Mars could have uninhabited habitats. So that's the idea, that it would be Mars colonized it, but then went extinct, or it never even colonized it. But although that's a possibility, we don't know yet for sure that they're uninhabited. And there's some inconclusive evidence suggesting life on Mars already. And this is a reanalysis of the Viking label release data, where it evolved radioisotope labelled gases from the organics that was fed to the dust, and this was detected here through the radioactivity. And you see the peaks right at the end, delayed right at the end beyond, and this is the height of the temperature. So it goes very high in temperature, and even a little bit later you've got the peaks of the actual evolution of the organics. It's also smoothed out a lot more. You haven't got it, that's got a double peak, for instance. This is just really a single peak. and you again kind of double peak and just a kind of single peak, not a very obvious double peak. This smoothing, and then the offset of the main part. So the main bulk of the temperature is here, the main bulk of the emission is there, which is 2 hours later. And to the trained eye of a biologist, that looks like life. And a few tens of minutes, Joseph Miller says, could be chemistry. But it's very hard to design, to imagine or work out any kind of chemistry would have such a long offset of 2 hours. So that's some of the strongest evidence there is for life on Mars right now. And yeah, I explained all that. So then, how could there be life on Mars? And do I explain a bit about the oxygen thing? Yes, I do. I'll do that in a bit. Right. So I have a new proposal. So the puzzle thing is that this is what Mars would have been like originally, and if we were 3 billion years ago, 4 billion years ago, then it would be no surprise to find life there. But that's what it's like now. Really, very hard to see how anything could be surviving there. It's quite surprising, and it's sort of beneath the surface of the dust with perchlorates that take up a little bit of moisture, 100% humidity at night. That's what makes it possible, because there's huge temperature difference day and night, because it hasn't got the insulating air of Earth's atmosphere, and then that leads to very high humidity at night, 100%, which then can be taken up by the salts, and then it's retained through to the daytime, and that's basically how those curiosity brines work. And perchlorates are very hygroscopic; they take up the water, the high saturation of water from the nighttime air. So even though it looks very deserted, it's not. It might be less of a desert than it seems to be. But how could it have stayed? It's at just the triple point of water. If it's just a little bit drier, there'd be no possibility of life there. So it seems remarkable that for 3 billion years, most of the last 3 billion years, it's been like this, not like that, nowhere near that. So if you think about the swansong biosphere, that's Jack O'Malley James's term, then it could well have had life there. Then it would have been a few 100 million years, maybe a billion years or so of swansong biosphere, but how could there be 3 billion years? This is where I've got a new idea. So my idea is that this would work not just for Mars, but a whole range of planets which produce quite a lot of CO2, but not quite enough. And if they have enough CO2 to have liquid water and lakes on the surface, but not vast amounts of CO2, and they're in a similar orbit to Mars, further away than the Earth, then, and a small planet like Mars, I don't know how general this would be, but then the idea is that it's not very sensitive to the amount of carbon dioxide they produce. And it's just the way that Earth, then it doesn't matter how much carbon dioxide the volcanoes produce, the photosynthesis reduces it so as to keep the biosphere at a certain level, but it's not actually optimal for Earth. Earth is rather cooler than the maximum, if you want to optimize for the maximum biomass, and be rather more than higher temperature than we have. And on Mars, this would be very much more so, because if you've got photosynthetic life, and you've got water and rivers that's taking out carbon dioxide from the atmosphere, it's going to cool down and cool down and cool down. And we keep on doing that until it's close to the triple point of water. So what we see now is what we'd expect. And it's even really a kind of biosignature for, I suggest this could even be a kind of biosignature, not for an individual planet, but for a class of planets. And if we were to start observing exoplanets, we find lots of Mars-like planets, and if they all have the atmosphere pretty close to the triple point of water, we might conclude from that quite a large fraction of them are probably life-bearing. Just like the detection of oxygen and methane or something in the same atmosphere in quite large quantities, this might be another kind of biosphere. And so the idea is that the same process would cool the planet down until it is limited by the absence of water. And then, as the tilted axis changes, or more CO2 is emitted in a great big increase, a great big pulse of CO2 added by a volcanic eruption, it might get warm enough for liquid water for a few million years, but soon all be drawn down again, and the atmosphere reverts to what we see today. So, if that was the situation, and then most of life would be impossible to detect from a distance in exoplanets, we might detect life at several times when it briefly greens a little, because of the extra emissions of changes in axial tilt. So this idea of that there's a process that keeps Mars close to the triple point of water, that's not new. But the papers I found only look at abiotic photosynthesis. So really, the only thing I've done here is say, well, what about, I just taken one letter away. I just removed one letter and changed abiotic to biotic photosynthesis. And then I said, what happens if you remove letter A? That's basically what I did. So it's quite a small thing here, really. And so, but I seem to be the first to have done it. I mean, at least in the published literature, maybe people chatted about it. And so the methane emissions, those could be self-limiting too, and this is gets very speculative. But Mars had methanogens and also maybe clathrates below the surface from ancient Mars, maybe deposited by life originally, maybe deposited abiotically. And then this is releasing methane in the present, and methane coming to the surface would warm up the Earth, warm up the surface if you had lots of it. And then methanotrophs could form calcite deposits, because that's the thing that happens when you have methanotrophs eating methane in these conditions, very similar to Mars conditions. Then they form calcite deposits that will block off the methane until the surface cools down again. And so just possibly the methane plumes found by Curiosity could be produced in this way. It's just an idea. I don't want to press too hard on that, but it's just an idea and interested any thoughts on the possibility. Anyway, the Curiosity found an excess of oxygen in summer of what you expect from chemistry and geology, and a deficit in winter. That's a recent discovery, I think earlier this year. And the oxygen also, surprisingly, there's more oxygen when the dust optical depth is there. You've got the oxygen there, and when you've got less dust, you've got more oxygen. It's not, it's a definite trend. There's nothing this low over here. There's nothing this high over there. It's suggestive that it might be that whatever it is, it involves photosynthesis. And of course it could be that abiotic photosynthesis and something else or whatever, but could it possibly be biotic photosynthesis that is doing that? So if there is, well, I actually checked on the cell count. I haven't got the cell count here. It's in my paper. I could look it up in a moment, but it's not really important what the actual cell count is, what the actual number is. But the cell count to produce those levels of oxygen, they are checking against literature, because there are papers on that topic. Then it's actually quite high. It's higher than the amount of life in the driest regions of Antarctica, but there were some evolved oxygen measurements where there was enough produced, and that was things like thin biofilms beneath gravel in rather more habitable conditions. But then, in some ways, Mars could be more habitable than the Antarctica dry valleys, if it does have these perchlorate brines below the surface, and because of the 100% humidity at night and the hygroscopic perchlorates. So if you imagine that it's actually really rather productive there, then you could get measurements like this. If that was the case, then drilling into the dust might have to return a significant amount of organics, and a quite high probability. And after all, both Vikings missions just landed randomly in the equatorial region, and they both just dug near to where they landed, and they both produced the label-released results. If there is life there, it would seem to be pretty pervasive in equatorial regions, and it might be that there's enough of it for this. None of our spacecraft since Viking would have been able to detect it. They haven't sent biosignature detection capabilities for the last 50 years, nearly 50 years. nearly half a decade, half a century. So I think there's an intriguing possibility, and all this makes it, so I was talking about how you could have a sterilized return. This all is motivation to actually return samples of liquid layers indirectly detected by curiosity. And Perseverance, sadly, can't do that, as far as I can tell. It drills into rocks and returns to sites dedicated, designed to drill into rocks. It's got a geological mindset behind it. Geologists love rocks. There are lots of rocks on Mars. We sent a rover to Mars to drill into rocks. And we make a specialist rover, and all it can do is drill into rocks. And that's basically what Perseverance does. And so I don't think we can really adapt Perseverance to, I think, gather that I hope, maybe just possibly, it could deposit, just go through its entire process but not drill anything, and deposit, and not cap it, put a cap on its capsule, on the sample tubes, and deposit the sample tube vertically in the sand, and then leave that, and then later on, the Esophage rover could gather that sample tube. You might wonder, what's the point? Well, the point is to gather the dust from the dust storms, because that's another thing of great interest. Because if there is any biology on Mars, then it would likely use the dust storms to spread. For instance, those biofilms that I mentioned, they're little fragments, tiny little fragments, maybe microns across, covered with nanopores of iron oxide. And perhaps we make like sporulating bodies, maybe not even spores, just very hard and very contained patches of the biofilm that would get blown across in the dust. And they wouldn't need to be levitated into the air. They could actually do these jumping great bounds across the surface. Forget the name for it, but you know, the dust grains that do that in the Sahara Desert, and they do great bounds across the surface, individual dust grains, and that's the main way the sand dunes move. And that's how they'd be moving on Mars as well. So quite big grains could be moved from one sand dune to another like that, with the biofilm enclosed with nanoparticles of iron oxide to protect it from the ultraviolet radiation. You can go on and elaborate all sorts of fanciful ideas. We don't know until we actually go and study there. But certainly the dust would seem to be of great interest. And so you'd also, for if we do have human colonization, then we want to know what dust is like, because it's likely to be quite hazardous to humans. It's got perchlorates returned to chlorates as a result of the UV, and it could knock humans unconscious. According to one paper I read, it's a potential possibility that breathing in Martian dust could make you go unconscious. So we really need to know what's in that dust. And then in terms of the planetary protection in the forward direction, we need to look at what happens to the whether terrestrial life can be spread across the surface. Perhaps terrestrial life could get into a little crack in the dust and then get blown at night in dust storms, or with the sun blocked out by the thickness of the dust storm. So you need to look at could that happen? So there should be a lot of interest, and it's not at all certain that I don't think Perseverance has got a dedicated dust collection thing. So it only if by chance some got into some of its sample tubes, which seems rather unlikely because the way it's designed with sample tubes underneath its body and the whole thing automated. Only if it got stuck on the outside, I think. So I suggest that the NASA, first of all, the Esophage rover, I think it should be adjusted to have a little scoop on it, if that's at all possible. It's got an arm already to pick up the samples, and perhaps this arm can be designed so it a dual purpose as a scoop. And once it's picked up all the samples from Perseverance for the geologists, then it will just scoop out some of the dust, some of the regolith, some of the what you call dirt, for that's Chris McKay, astrobiologist, and he suggested that we don't need to do all this, that if we want to do something of interest with astrobiology right away, just have one day on the surface tops, scoop up a sample of dust and return it to Earth, So if we had a mission designed by astrobiologists, that's what they would have done. It would have spent just a day on the surface of Mars. It would be a much lower cost mission, and basically the Mars Ascent vehicle that we're going to send to Mars, it would be just that mission, plus a little arm to scoop up some dust and put it on board, and then take it back to Earth. So I suggest that we do a simple modification of the Esophage rover to basically turn it plus the Mars Ascent vehicle into Chris McKay's scoop a sample of dirt and bring it back. So I suggest we try and add a scoop to it. This is in the process of being designed by ESO right now, and they want to launch it in about 5 or 6 years' time. So the sooner the better for any such modification, if anyone's interested, start thinking about it. And then I also suggest, and then this shows how you could put it on top of, so this is a design of the sample return container, and they could put a plate on top and just pile the dust on top, or indeed, since the sample tubes are all going to be capped, then maybe you just pour it on top of the sample tubes and it falls through in between them. It doesn't really matter much, so you just want a sample of the dust, and quite a large sample, the larger the better. A sample of the dirt, and especially digging down to 5 centimeters, and in the sand dunes if you possibly can, so that you can dig into where the bind layer is thought to be, and where footage. It doesn't seem like you have to be very precise, because remember, both Viking landers dug up, and if that was life they discovered, then it seems that you just go and dig up a pile of dust almost anywhere. And if it isn't life, then we make huge progress in understanding the chemistry of whatever it was that led to those strange signals for the Viking lander, and then that helps us to hone down, because eventually we're going to have to send instruments in situ to look for life if we don't find it now. And those instruments, then we want to design them so they don't get puzzled in the way that Viking did. So we definitely want to understand what Viking spotted. And so in all ways this is an interesting sample to return for astrobiologists. And then for the geologists, then both the dirt and the dust storm, they're like miniature geological samples of the dust storm spread over the entire surface of Mars. So it'll be tiny geological samples, and I know that geologists studying an individual dust grain can get a huge amount from it, and from over the entire surface of Mars. So even considered as pure geology, then returning a scoop of dirt and returning a sample of dust would be of a great deal of interest, I believe. So then I also suggest that Esophage rover, if the geologists can be persuaded to sacrifice 1 sample tube or maybe 2 sample tubes for dust, then I suggest that if only there was a way of putting one inside the other, because you wouldn't necessarily fill it with dust, but you'd have a special one with a magnet at the bottom. And if that's vertical, then it will attract the iron oxide dust into the tube as it falls, because that's what's been discovered in the past, that when you have magnets on the surface of the rovers, you get a little pile of dust on top of it. So that's where the dust falls, preferentially compared with the places where there aren't magnets around them. So put a magnet in the bottom of the sample tube, leave it upright on the surface of Mars before you head off on your mission, and when you come back, then all the dust storms that have happened since then, or the dust devils or anything that's brought dust, then there'll be dust in it. I think that'll be another interesting sample. So that's all about that. And so it'd be great if Perseverance could do the same, but I don't really see how it can. If you look at my paper as it is now, I've got a suggestion for Perseverance to do that, but on reflection, and then on looking how they do the sample caching, I don't think it can. But if any of you know more about that, do say. So then, this could transform what is a really mission that is not of great interest to astrobiologists. It's of some interest, but basically it's adding more of the Mars meteorites we already have, with ambiguous biosignatures. As I said last time, the Perseverance will not be able to detect the signatures, the samples there that are as interesting as the Martian meteorites we already have. You wouldn't be able to detect the biosignatures that we find so interesting in distant meteorite and the LH 84001 meteorite. So it would really only be by chance that we return instruments, meteorites, samples as interesting as those two, of all the ones we have. So, but if there's a high chance of returning life, and so this, looking for getting present-day life, though, if our reasoning is correct, and perhaps the Rosalind Franklin, the ESA rover, and perhaps Perseverance, they're going to be making new discoveries for sure. So, who knows, maybe they reinforce the possibility that there may be life there, present-day life. If we think there's a good high chance of returning life, then what do we do? We can't, if you accept the conclusions of my previous talk, we can't return it to the Earth's surface. So, then not with present-day technology. So we could do if we know what's in it, and we know how to protect against it, but the very first samples for sure we can't return. So we don't have the time, and also the precaution prohibitive principle might even get invoked at some point in any legal process. So I suggest the safest place is to the Earth's ring plane. So this is just a kind of diagram to just show the idea. It's actually way, way further out. It's a geostationary orbit. Near Earth, it's in equatorial plane. It goes up to the it curves up to the ecliptic plane, where the rings are, as you go to infinity, and so halfway in between the two, it's about 7 degrees to the equatorial plane when you get to above GEO. Because the advantage of that, and I found a paper that was looking at the best disposal orbits for geostationary Earth orbit satellites, and it said that the Laplace plane is the best place, because any particles that are thrown off these satellites would not come back to geostationary orbit. Geostationary Earth orbit, that's what I've been looking for. Yeah, and this is it, and it's because it's constrained in the phase space of both the inclination and the argument to the ascending node, and then the eccentricity is also constrained in a particular interesting way, and from all that they conclude that it wouldn't impact into the equatorial orbit satellites. So I'd suggest in the Laplace plane about 10,000, so even where the two intersect, it seems it doesn't do that. And so I suggest returning it to maybe 10,000 kilometers above geostationary Earth orbit. And then I also looked at a way it could return. You can find the details in the paper. Then there's a very low energy way of sending spacecraft from Earth to Mars. The most efficient way seems to be to use a halo orbit around the Earth-Moon L2. That's the point of gravitational equilibrium on the far side of the Moon, where the Earth and the Moon's gravity balance. The halo orbit is like a circular orbit around that, where it just goes. It's actually orbiting around the Earth, but as it orbits around the Earth in the Earth-Moon system, then it actually goes a little bit of a circle around that state, that point of equilibrium. If you use the Earth-Moon's if you use the Earth-Moon as your reference frame, and then from the halo orbit, it turns out if you position it in the halo orbit just beyond the Earth-Moon L2, then it'll gradually spiral out and out and out and out, and get faster and faster away from Earth. Now, if you time that just right, it'll end up eventually just beyond the Sun-Earth L2, and then it gets into the Sun-Earth L2 halo, where now it's the Moon goes on its thing, but this is always constantly opposite the opposite side of the Sun from Earth. Then it starts doing a big halo around that as well. It goes out and out and out, and eventually it ends up with Mars with quite a lot of extra delta V they just got for free. So if you can do that in reverse from Mars back to Earth, and the ESA orbiter, it's got electropropulsion, So it would certainly be able to do this very easily. It would just need the delta V to go back to that halo orbit of the Earth-Sun halo, and then to the Earth-Moon halo. And so it won't be very few times when you can use that particular very efficient method. There are various other methods you can use as well, which are also pretty efficient. And the great advantage of this one is it never comes anywhere near Earth. So very good in terms of planetary protection. Although I do think that a flyby, as long as it's sufficiently distant and nowhere near our satellites, then we are very good at flybys as well. But this would be very, very, very good for planetary protection. And so it ends up in this orbit, never coming anywhere near Earth. Once you're at the Moon and LL2, and then you can move to the near side, and then you can find an orbit that takes you down to above GEO with really not that much. Certainly, and also fantastic looping orbits. They exploit the Earth, Moon, Sun gravitational fields. So there'd be very efficient ways of getting it down to GEO as well. So I suggest that would be the way to do it. So we then have the satellite above GEO, and I think I've got another half hour. I think half an hour. I'll stop soon, and then I'll do the last one. I'll have 3 of these. So above GEO, then you study it by teleoperated in situ studies of samples in the satellite. So basically, I mentioned in the previous video all the instruments that astrobiologists would like to send to Mars. Well, we can send them up to this. Tiny, tiny little things, miniature electron microscopes, miniature DNA sequencers that do the whole end sequencing from beginning to end, and miniature, and then miniature analysis that can detect a single amino acid in the sample, in a gram of sample, and some extraordinary instruments that the astrobiologists have designed to send to Mars. Well, we can send them. They haven't been sent to Mars, but we can send them to look at this sample in orbit. The very first thing that would happen as soon as it gets there, then you would have a mission that comes from Earth, goes up there, takes a little bit of the dust and a little bit of each sample, sterilizes them, and then returns them to Earth. And so that is the same as the sterilized mission, with only a few weeks difference, or maybe a month or 2, because you've got all the halo thing as well. You slow it down a bit, but it's certainly not years. So you just delay it a bit. You still get all the geological samples you were going to, but you've left unsterilized versions of them up in orbit, which you can then study as you like. And then, depending on what we find there, if it's not as interesting as it seemed it was going to be, and if there seems to be no life there, you sterilize the whole thing, bring it back to Earth, and that's it. And it's basically a sterilized mission, but with just a bit of a wait above GEO for a while you decided what to do. But if you found Martian river life in the sample, then I think just about everyone would agree we simply don't have the technology to return it to Earth. So in that case, it would become the nucleus of a new laboratory using only telerobotics that would study it remotely above GEO, and then would be totally safe. And everybody would say, oh, but isn't that good that we didn't return it? Because we don't know how to contain mirror life. Not to that level of assurance. And so you then do whatever is needed to protect Earth, depending on what you find. And it's not necessarily going to be hazardous to Earth. So the entire archaea is the entire group of archaea, an entire branch of life that is not pathogenic to humans, not pathogenic to higher life forms. It seems if it is, it's very, very rare. The worst is maybe it may be slightly involved in toothache, in tooth decay. That's about it. It's not really nothing very serious, only along with other things. So that's an entire domain of life. And so you could imagine an entire domain of life from Mars in the very optimistic scenario. which when introduced to Earth is only beneficial. And even though it ends up being everywhere in the soil, in the sea, on your skin and everywhere, it doesn't do any harm. And that would seem so. I mean, then in other situations would be that you return life that is a very early form of life that you figure out is just not going to be able to survive on Earth for some reason. And there are various other scenarios where you could decide that we really don't need to do very much to protect Earth. There'd be other ones where you need to do a huge amount to protect Earth. And we need to have really good knowledge, because we need to also know what would happen after it evolves, after it gets back to Earth. Not just what it is right away, but if we introduce the terrestrial biosphere, then it starts to evolve and diversify, then will this be good for the terrestrial biosphere? So there'd be quite a lot of thought needed returning exobiology. Anyway, I'm going to think a little bit more about those sort of things. So I basically decided that I've explained all that. And so, how much have I got left? Oh, I haven't got much left. Oh well, so I'll just finish this another few minutes. And if you find mirror life, yes, I explained all that. So Mars colonization enthusiasts, they tend to assume that Martian microbes are bound to be safe for Earth, and terrestrial life bound to be safe for Mars. And then the precautions we need to take for planetary protection can seem like pointless red tape, with an obvious outcome that we later show it's unnecessary to do. It was never needed to be done, as for the Moon. Basically, they're thinking in terms of Mars is going to be like the Moon. And we had all these things, plough we did for the Moon, it wasn't needed. And the Mars colonization enthusiasts quite naturally. And I used to think like that. Before I became aware of, I had a little compartment in my mind between, we've got to protect the spacecraft, of course, got to protect Mars from any Martian life from the spacecraft we send there. But then once you send humans there, why would you need to protect it from humans? Humans just would go around and do their usual thing they do on Earth. So you have two little domains of thought that don't actually have much communication with each other. Where you say, of course you sterilize the instruments you send there and the spacecraft. But humans, they go around doing biology on Earth. Why would you need to sterilize, do anything with the humans? And you don't put those two together. But it's actually not necessarily safe to send humans to Mars, both for Mars and for Earth's biosphere. So, I mentioned about the domain of our care. So, if the Martian life can't be returned to Earth, I should say Earth, not Mars, this will be frustrating in some ways. I often do that. I type or say the wrong word. If I say some very unexpected word, then that's probably me doing that same thing. Hopefully I haven't. Reading the text there some of the time helps a bit with that. Anyway, that would be frustrating in some ways, but we still have the Moon, which has great commercial value and it's a better destination for humans in many ways. So I mentioned that the people keep on using the analogy of going to Mars like going to the Americas from Earth. Well, the earlier settlers in the Americas could use the same technology as the Old World. Once powers still worked and so on, they could grow crops in the soil, and the fur trade was immediately lucrative from the get-go, and the land they colonized was already inhabited by humans. And the Moon, so if you look at Mars, then none of that really applies. If you look at the Moon, it does have some potential commercial value for platinum, and ice to supply to LEO, and for tourism, and then the scientists going there as well. In a decade or two we might be able to take a 1-week trip to the Moon in either rockets or space planes. So although there aren't humans there already, there might be humans there quite soon, in the form of the tourists. And then they would set it up in order to be able to have their hotels and so on. And Mars has no commercial potential, and the challenges for agriculture are the same for both Mars and the Moon. You can't just plant a seed in either the Martian or the lunar soil and expect it to sprout. And the hard vacuum on the Moon, and people do talk about how you might be able to get lichens growing on Mars. It's really very only in semi-shade, not in full sunlight. And you can't really get an awful lot of food from bits of lichen that are growing in semi-shade, even if it is possible it might be there already. So really the agriculture is pretty much the same for both. And if you look at making a greenhouse, then an ordinary greenhouse put on either Mars or the Moon, it would just explode from the atmospheric pressure. So you have to build something much more robust than a normal greenhouse. And the grey rather than the red dust means that the iron on the Moon hasn't rusted. That's beneficial. It looks less Earth-like, the Moon. But the grey dust actually means that it's actually a more attractive place to be. Because what's the use having those nodes of rust? And unrusted iron is much better than rusted iron. And then the hard vacuum on the Moon are very useful for making, they're better than the best terrestrial labs for making chips and solar panels. And then you have the peaks of almost eternal light, the lunar poles, with almost constant temperature, and sunlight 24/7 as well, nearly year round. And the lava tube caves on the Moon are likely to be larger than on the Moon, Mars, several kilometres in diameter. I discuss all this in much more detail in my case for the Moon first. But anyway, so the Moon is a great place to explore first, and there are many books about colonising the Moon, but they don't have a charismatic advocate in the same way. Robert Supin and Elon Musk are very charismatic, and they get a lot of people who want to follow them. But I think the Moon is actually more interesting, and part of it is just that we've been there, done that, which isn't actually what Buzz Aldrin actually said. He was misquoted, he didn't mean it like that. He meant it as a joke, not as a serious thing. And Buzz Aldrin certainly thinks we should go to the Moon first, as well as Mars. No matter how, even though he's very keen on Mars, he sees the tremendous practical value in going to the Moon. And so, if you have that, well, been there, done that, then been to Mars, done that. It's not a very good way to have a long-lasting colony if you haven't been there, done that attitude, that we're not going to colonise the Moon because we've already been there. Then as soon as you go on to Mars, you say, well, we're not going to colonise Mars because we've already been there. Where should we go next? Callisto. Callisto is an excellent place to go. I recommend going straight to Callisto if you're going to be doing a been there, done that approach to colonisation. Anyway, not that you can, it's a little bit difficult to get there so quickly. But anyway, I'm being a little bit, maybe slightly facetious there, sorry, but I don't mean it in a nasty way. I'm just saying that, that I'm just putting it more in a positive way, that the Moon has a lot of potential. And then if it turns out that Mars is just not safe for humans to land, because if there's no life on Mars, and if we can never return it to Earth, then that means anyone who lands on Mars most likely can never return to Earth, because they can't bring mirror life back to Earth, and it would likely get into their microbiome, even if it's not dangerous to them on the surface of Mars, which it could be. And then it's certainly well possible that whatever's there is harmful to humans. So we absolutely, as space colonization enthusiasts, have to know what's there before they really can make proper plans. And so I think once we get to Mars, if it's interesting biology, that can unlock billions of dollars of extra funding and settlements, and they could use materials from Phobos and Deimos, the two moons of Mars, and study it from orbit by telepresence using robotic avatars on the surface. And Mars is spectacular from orbit, especially if you use something like the Hera orbit, which is one of the early ones you choose, which comes to the near to the surface of Mars, skimming right close to the atmosphere twice a day, and then skims past the lunar poles. And it's one of these trapped orbits that's sun-synchronous, and it's at a high inclination. Very, very interesting orbit. And then you go away, and Mars retreats to be a tiny planet in the distance, and then you come zooming in again 12 hours later in the second time. You do that twice a day. It's a really nice orbit, very spectacular, very interesting to explore Mars from orbit there that way. And so, and then and many other colonization targets, including Jupiter's Callisto. There's also, I should mention, there's enough material in the asteroid belt to make habitats spinning slowly for artificial gravity with 1,000 times the surface area of Earth. And this is the way Asimov thought. Carl Sagan, was it him? I don't remember where he got it from, the idea of the term planetary chauvinist. It's the idea that actually there's much more colonization space in between the planets than there is on the planets, which is a very inefficient way, because you create gravity by piling up huge amounts of mass that's not used for anything except to create gravity. It's much more efficient to make a space settlement using materials in space. And I mean, like if you dismantle Mars or into space settlements, you get a vast area. That way, far more than you can get just living on the surface. So anyway, I hope that the colonization enthusiasts and the astrobiologists can work on this together with their mutual interest and the benefit of Earth as a whole. And with Mars, a far higher level of technology is needed than for the continental shelves below the sea, which are not yet inhabited. And I mentioned that bit about the greenhouse, and that's where you can download my preprint. And so that's just a section of some of the things from my paper that I've mentioned. There's a huge amount more in there if you go and have a listen to read of it. And I'm very interested in any comments, any suggestions, any ideas, mistakes. Don't spare any blushes. If I've got anything wrong, even if it's something elementary and it's silly, don't worry, please just let me know. I'm very interested in immediate comments on this video, or if any of you are interested to have a look in detail at the paper, and if anything you see there in any particular section is of special interest to you. And I'm very interested to chat about it and hear your ideas, and I could give more video talks like this if anyone's interested on any of the particular things that I cover there. It's quite a long paper. It's quite a difficult one to write because it's so multidisciplinary, and that's why I'm especially interested to get lots of feedback. I'm multidisciplinary. It was an astrobiologist friend who suggested that I write this paper, and it will be, if it gets published, my first astrobiology paper. And so, anyway, I was interested to hear any comments on it. But it's so multidisciplinary, but I think it obviously is one to try to send to astrobiology journals, because the most technical stuff is in the astrobiology, and I've been tried talking to people. Please have a look at it and see if there's see what you make of it all. Very interested in comments on it, and so I feel that this is quite timely, because if what I say is correct, then NASA shouldn't even start on the legal process. It's just a waste of time. There's no way they're going to succeed. So they should be thinking about how to do the sterilizing the sample return, or to return it above GEO. And this would save them vast amount of money, vast amount of time. They don't have to build the sample receiving laboratory. They can only build what's needed as time goes on. And you always have to think that if your mission, it might even fail. You don't want to start on things until you know that they're needed. Well, this works like that. That it's only once the sample returns to above GEO that you actually will start building things to send up there. You can even, and if take a simple example. Suppose you find that there seems to be life in the satellite within the sample that you returned in the dust. And suppose this life is mirror life, and it doesn't use the same nucleotides as terrestrial life. Then you will want to find a way to sequence the mirror DNA. And that is not something, you're not likely to send something to Mars that's able to sequence mirror DNA of that particular type. It might take quite a lot of research to learn how to sequence mirror DNA at all. And then once you've done that, you also you might have to deal with different nucleotides. So that is something which you could work on Earth, and then as soon as you got it, you can send it up to the satellite. You don't need to send it all the way to Mars. So there'd be all sorts of things like that where you make discoveries, and based on the discoveries you decide, oh, well, I've got to send this up there, and you can do it. And you can go up there, and especially with the technology we have by the 2030s, which is when this will be returned, we'll be able to send huge, huge masses up there to above GEO. And we'll probably be flying back and forth to the moon by then. You never know. And this will just be a kind of stop off, but humans must never go near this orbit because of the possibility if it's got mirror life. So you've got to be careful where you situate it. Thinking forward to the future, are we going to need to put other things in there? And maybe 10,000 kilometers above GEO is too close. Maybe it should be double the height. Maybe it should be 60,000, 30,000 kilometers. Maybe it should be 70,000 kilometers above Earth's surface. Just well away from GEO, but still awful long way away from the moon, or even further. So we need to start thinking about these things, if that's what we're going to do. And then I do think that modifying the Esophage Rover to add those things. Anyway, they're very interested. If that's a possibility, could we add a scoop to the Esophage Rover? Could we add? Surely we could add a sample, a container with a magnet in the bottom to collect the dust. So something to give some thought into. Just remind again that. So I'll put a link to this in the video description, and it's got a link to the paper. I'll probably put a link to the paper in the video description as well.